Hi, my name is Julian Hunt. I'm going to present my research on global resource potential for seasonal pump storage and for energy and water storage in the International Conference on Water Resource and Environment 2020. I work at the International Institute for Applied Systems Analysis, the Sustainable Service Systems Research Group. This presentation presents results from the paper with the same name published in Nature Communications in 2020. So what's pump storage? Pump storage consists of a lower reservoir pump where stored water, which is pumped to an upper reservoir, storing water and electricity. When you need water or electricity, the water pump flows from the upper reservoir to the lower reservoir, generating electricity. So pump storage used to be the main technology for providing power for Europe, for the US, for Japan, the so-called developed nations, until 1990s. What happened in 1990? You see that after 1990, you had that pump storage stopped being developed considerably, just starting to be developed by China on the after 2000s. But why Europe, US, and Japan stopped investing in pump storage? They stopped investing in pump storage because of the collapse of the Soviet Union. So, with the collapse of the Soviet Union, the Western countries decided to invest in natural gas instead because they could control the natural gas market and so make a lot of money with the natural gas industry, which they did. And that in order to create demand for the natural gas, they had to create very strong lobby against hydropower and against pump storage and stop this rapid rise in pump storage. But now, with war in Ukraine, we'll have a scenario that we won't have natural gas in Europe, for example, anymore. And then Europe will have to invest again in pump storage, which is the second cheapest alternative for power generation and also for long-term energy storage. So the international view on hydropower is do what I say, don't do what I do. What does it mean? It means that the North America, Europe, and Japan already have explored all its potential for hydropower, and so they generate a lot of electricity with the rivers. But whoever wants to develop hydropower now can't do it. It's not viable. It's bad for the environment. And there's a strong, very very strong lobby against hydropower. And this one of the reasons is to maintain the developed countries developed so that they can have to buy natural resources like fossil fuels, oil, gas in order to fulfill their energy needs. And this prices and this market is controlled by both the US, Europe. So what's the motivation on pump storage? So pump storage can be applied for daily storage if you have thermal power, for example, coal power plant or nuclear power plant, or you want to store solar energy from a city or decentralized or centralized solar. You will have you will build a daily pump storage. In Germany, for example, there is a lot of daily pump storage plants because they have a lot of coal generation. For example, if you want to store wind power has a certain variation of generation which is properly stored with weekly storage pump storage plants. Switzerland and Austria has some capacity for weekly pump storage, and they are planning to build a lot more to store wind power. In For hydropower, for example, you can have monthly storage pump storage plants, which have the reservoirs are bigger, the dams are higher, the reservoir area is larger in order to store more volume of water, more energy. And then you can store wind power, hydropower, and these are the Switzerland and Austria has the highest capacity of monthly pump storage plants. And you also have the seasonal pump storage plants, which store hydropower, which store a lot of energy seasonally, which is which is good for complementing hydropower generation, water storage, and also seasonal variation from wind power, seasonal variation from from solar power, and also demand. So reservoirs for pump storage or for hydropower, they should have this conformation, which is that the level of the reservoir there has a very high level variation, but a very small area variation. So it should be built in a valley region where you won't have this degraded land. And at all costs, it should be avoided to have reservoirs where have very small level variations and very large depleted land. So when the reservoir is low, you have this depleted land. This should be avoided the most. So effective and good reservoirs have this profile. This profile will result in reservoirs with a very low flooded area, very high water storage capacity, and low evaporation losses. Also, you add these seasonal pump storage plants together with a cascade of hydropower plants. Conventional hydropower plants, they store the water in the river itself. This is the conformation of storage reservoirs. You have a large flow of water in your river, you store in conventional hydropower plants, and then you release the water to maintain a regular flow of water to the dams downstream. For seasonal pump storage plants is similar, but instead of storing the water in the main river, you pump to the to a reservoir parallel to the river in a tributary river, and you can also regulate the flow of the river. So how does it work? You have a powerhouse where water from a lower reservoir is pumped to the upper reservoir, and you have this large level variation, which can vary from 40 to 300 meters. The higher, no, from 30 to 150 meters, the higher the level variation, more water you can store in a smaller land. So comparing conventional reservoir dams with seasonal pump storage plants, you have that by storing an X amount of water, you store Y amount of energy and require Z amount of land with conventional reservoir dams. If you look at seasonal pump storage plants, you have the same X amount of water stored. You store much more energy, so 2 or 3 or 4 Y amount of energy storage. You require some energy to pump the water up and then generate the electricity down, so you have a little bit of losses. But the land use that you require can reach up to 10 times smaller. So Z would be 10 times smaller for seasonal pump storage because of the high level variation that you can attain with these types of projects. So for this paper, I developed a, a model which uses global topography data, global river network data, and river discharge data. And I look for the locations where you can build dams close to a river, and then you optimize the dam, you flood the reservoir, you create reservoirs, and then you estimate the cost for the reservoirs, the cost for energy storage, the cost for water storage, the cost for power storage. And yes, I published in the paper. So looking at the results, you have that the location with the highest potential for energy storage is China and India, and then you have the Andes region also. So, for example, storing energy with the cascade. So, assuming the dams in cascade, you have costs of energy storage from 1.5 US dollars per megawatt hour to 50 US dollars per megawatt hour. Comparing with batteries, for example, a battery, the cost for storing energy with battery is around 200 kilowatts per megawatt hour. So it's more than 10,000 times cheaper to store energy with seasonal pump storage compared with batteries. So this makes the seasonal pump storage a viable alternative for seasonal storage because it's 10,000 times cheaper than batteries. So you can store energy for 1 year, for 2 years, for 3 years, and it still be a viable solution. If you don't include the dams downstream, the seasonal pump storage plants, then the cost increases. And then you have projects as cheap as 4.5 US dollars per megawatt hour. So the continent with the highest potential is Asia, then is South America, then is Europe, it's no, North America, Europe, Africa, Central America, and also looking at other results, we have that the power costs are very low in very steep mountainous regions. So we have, for example, 370 US dollars per kilowatt of installed capacity. This graph shows that apart from storing energy, you also have some inflow in these rivers. So some of the rivers have the reservoirs fill up 100% with the water intake from the river, which would be equivalent to a hydropower plant. So these cases are hydropower plants. The more water inflow, the more hydropower you generate. The less water inflow, the more you have to pump to fill up the reservoir. These are the costs for the power costs for pumping. These steps vary because the model as you have a 3 kilometers distance for the tunnel. It increases 3 by 3. So it looks for 3 kilometers, then 6, then 9, then 12. So these are the reasons why you have these steps because of the way the model is developed. And you have the flooded area. So you have some locations where the flooded area, the amount of area you require for energy storage, for example, in the Andes is very low. In the Himalayas is very low. The amount of land that you require to store. Other locations, the amount of land is slightly higher. The amount of land required to store energy depends on the level variation, so the topography. The more steep the topography, the more mountains you have, the less amount of land you need to store energy. Looking at the cost of the projects, you have the dam cost, in average is 35% of the project cost. The tunnels are 40%. The land is 5%. For the land cost, I assume the cost of land in Holland, the Netherlands, which is the most expensive land cost in the world. And I do that just to show that the land cost is very low compared to the other components and to show that land is not a problem in this case. You just have to make sure that your land is available to be flooded. Then the turbine cost is 5%, electric cost 11%, and excavation cost 4%. Then you have the dam height. If you increase the dam height of your project, you can store more water. but it might reach the point that you have no more water in your river to fill up the reservoir. So the model also takes into account the benefits from storing water. If you can't, if you don't have enough water to fill up the reservoir, then the cost of the dam, if you increase the cost of the altitude of the dam, the cost will increase, and the cost of energy storage will increase again. So you have an optimal height because it takes into account topography, the cost of the project, and the amount of water that you have to store. This is a project, an example in the Gorigabu River, which is in China, and you can use this reservoir in parallel. Here, the dam will be too expensive and long, and you will result in a lot of evaporation, so you can store water in a tributary river, which will be very cheap. This is the example of the project. You have the powerhouse, you have the tunnel connected to the reservoir and the dam. The results from um, this paper are available for free if you want in this website. So you can go through all the projects. You can click at the expensive, cheap projects around the world. So there are several projects that you can see. I have also took part of a project on Brazil, and we created another map. So this is a more developed, so it's a better version of the model to map seasonal pump storage plants. And to finish off, there is an interesting project that you can do with seasonal pump storage, combining the two most important basins in China. In the middle, you have a seasonal pump storage plant, which you can transpose water from the Yangtze River to the Yellow River and store a lot of energy seasonally at the same time with a reservoir in the middle. You transpose water, you store energy seasonally, and then you bring water from the Yangtze River to Yellow River on its head of the river, which is quite interesting. So it's just a very interesting project that should be considered. So in conclusion, we have that 95% of current storage capacity in the world is based on pump storage. Seasonal storage is important to store solar energy during the summer to use during the winter. Seasonal storage can be used to reduce seasonality of natural gas imports. Seasonal pump storage optimizes the hydropower potential of hydropower dams downstream. It's the cheapest way of seasonal storage. It's not only it does not store only energy, or it also stores water, reduces floods, and improve water management. There is a possibility of water transposition between different basins. China is the country with the highest potential of seasonal pump storage in the world. China is currently building 35 gigawatts of installed capacity of pump storage in order to increase its energy security, and they should focus on seasonal pump storage. Thank you for your time. Bye bye.